important topics related to our open VSP, the basic fundamentals we have covered, right? So today we will be dealing with the next topic, that is creating a basic wing model. Whatever so far we have discussed related to the basic fundamental, especially related to our open VSP, the fundamentals. Now we have to use those fundamentals step by step to create our models. That is the wing model, fuselage, empennage section, engine. Like that we have different components, right? So first we will design the wing model, then we'll go for step by step to other components. Okay. So today I'll be telling the basic modeling process. Okay. Related to the wing. So how to create a basic wing model. Okay. So you may get the question like this. What is that question? By using NASA's Open VSP software, design a basic wing model as per the given wing data or parameters. So we have the parameters. What is that? The first parameter, which means the given data, wing reference or platform area. Generally, we will call that as S. That is 60 meters square. A material, aluminum based material, which means you have to design a model. Okay, the model material should be aluminum based. Okay, and aerofoil, you have to use this aerofoil NACA 2421 aerofoil, and the chord of that aerofoil length must be 2 meter. Tip chord length 0.8 meter. Root chord length 3.2 meter, which means this is our root chord and this is our tip chord, and overall platform area, that is 60 meters square. And sweep angle, what we have, this sweep angle, that is 30 degree. Okay, so this is our given data. As per the given data, we have to do this process in our open VSP, which means we have to design the wing model by using our open VSP. So as we know, the given model is in this form, that is the aerofoil. We have to use NACA 2421. So here, what aerofoil we have? The aerofoil is a 4-digit aerofoil. Okay, NACA. As we all know, NACA in the sense National Advisory Committee for Aeronautics. They do aeronautical research related work. Okay, now commonly we will call NASA. Right. So here, National Aeronautics and Space Administrative renamed for this NACA. Okay. So the aerofoil what we have, that is 4 series aerofoil 2421. 2421, right? So 4-digit aerofoil, as we know. Okay, that first digit, it will tell you about the camber in percentage of chord, which means 2% of the camber, and the location of camber 40% from the leading edge, and last 2 digit that will tell about the maximum thickness, right? So here, before going to design the model, just I'll tell you about the aerofoil, because that is very important thing. These all things I have already discussed about the parameters. Okay, so these all parameters is not required. Just we will use these parameters to design a basic wing model. We are not going to any complicated. We have to create a basic wing model, that's it, as per the given data. Okay, remaining everything will be as it is, whatever we have in the OpenVSP software. Okay, yeah. So as we know, aerofoil, the given aerofoil is 2421. Okay, so for this case, if we take the cross sections of our wing, this is our aerofoil. This aerofoil will look like this. Okay, so these are the nomenclatures of our aerofoil. We will call this one as our leading edge. Okay, the nose part, but we have the aerofoil leading edge, the front section of leading part of our aerofoil. Okay, the nose type of section what we have, that we will call the leading edge, and the end part what we have, that we will call the tailing edge, like a tail kind of thing. Okay, so that's why we are calling it a trailing edge of an aerofoil, and the upper surface of our aerofoil, the curved section what we have, this one, this is the upper surface of an aerofoil or upper camber. Okay, and this one is our lower camber, and the straight line what we have from the leading edge to the trailing edge, the straight line what we have, this one, this straight line is called as the chord or chord line. Okay, and the equidistance line, the dotted line what we have, that is the equidistance line. Okay, if we cut along this line, then we'll get 50% aerofoil over the upper surface and lower surface. So that's why we are calling this is the mean camber line. Okay, or equidistance line. So for this deeply we can go that, as we know, the given aerofoil is 2421. Okay, for this case, this one what we have, the leading edge to trailing edge statement, that is our chord line, as I told you. Okay, the first digit what we have, the 2, it will tell you about the percentage of camber. Okay, percentage of camber in the sense this C max, this one, how much camber you have for this particular file, that is 2% of camber in percentage of chord, that is 2%. And next digit what we have, 4, that is the location of the camber from leading edge where it is located. Okay, 4 in the sense the 40% from the leading edge. Okay, which means the second digit what we have, the 2, that is the location of the camber from leading edge. Okay, this is that our xc, that is the location of camber from leading edge. And last two digit what we have, 21, that is the maximum thickness. Okay, this complete part from this lower camber to upper camber surface what we have, the complete distance, that is the maximum thickness t in percentage of chord. Okay, and from leading edge to trailing edge what we have, the complete distance, that is our chord length. Okay, so that is what just now whatever I have discussed, everything is given here. If you want, you can take a screenshot of this. Okay, so this is our leading edge radius, the maximum thickness. This this is our maximum thickness, right? And this one is our maximum camber. Okay, in our case, in our given data what we have, percentage of camber 2%. Okay, and location of camber 40%, and thickness of aerofoil 21%. Okay, which means this one, camber is 2%, location of the camber is 40% from the leading edge, and the maximum thickness of the aerofoil is 21%. Okay, so this is our chord line, and this is the mean camber line. This one is the leading edge and the trailing edge. The straight line what we have from leading edge to trailing edge, that is our chord length. Okay, chord C. Generally we will call it as C. So see whatever I told about the aerofoil, what we have in our given data. Okay, that aerofoil, the first digit, that is the maximum camber in. Okay, 2% of 2D aerofoil, and second digit what we have, that is the location of the camber. Okay, and last two digit that will give you about the maximum thickness. Okay, so this is what we have, this scenario for our case. Okay, so according to our given data, the camber thickness is 0.02 meter, 2%. Okay, 2% in the sense 0.02 meter. That what we have here in terms of 1 meter chord length, but in our case we have the chord length that is 2 meter. Okay, which means that will be double of that. So we will use this all data to design our basic wing model. Okay, and we have rest other things also. Okay, so whatever we have to design the wing, that will come under this type of aeroplanes. Okay, see our given data. Okay, so this wing model what we have, the 2D diagram, that will match to this kind of aircraft, which means commercial related aircraft. Okay, and it's like a swept back wing. Okay, yeah. So now we have to go to open VSP. We all know all these parameters to design our wing model. Okay, just recap these things which I already discussed in my previous class. So we have to go for open VSP. Okay, so I'll come to the given data. Yeah, now what we have to do, first we have to select the wing. Okay, and we have to add. As soon as we select and as soon as we add, then we'll get one default wing in our open VSP window. This is our open VSP window or main window, and this is our geometrical window. Okay, and this one is our component window. Which component window? The wing component window. Now what we have to do, we have to use these parameters. Wing reference area 60 meter square. So now what we have to do, we have to go to, yeah, first we have to change the wing reference area that is 60. Okay, here default we have value. Okay, this all thing is a default value. Okay, so for this default value we have to design our wing model. Okay, this wing model by using NASA's open VSP software, design a basic wing model as per the given data or as per the given wing data or parameters. So first we will import these parameters, that is wing reference area or platform area 60 meter square. So here we have the area that is 60, just type 60 and enter. Okay, and next what we have, the material. Okay, let I'll import this aerofoil, that is NACA 2421. Now what we have to do, we have to come to aerofoil and we have to, okay, see here we have to change the aerofoil. It's already 460 aerofoil, but as per our requirement is not there. Okay, default we have some other aerofoil. So for this default aerofoil we have to change according to our requirement, that is NACA 2421. Okay, so to do that, what we have to do, we have to change the thickness to chord ratio, camber, percentage of camber, and camber location. Okay, so as per our requirement we have the camber that is 2%. Okay, just we have to import that 2% camber here, that is 0.02, enter. Okay, and next location of camber, location of camber, that is 40%. Second digit that will indicate the location of camber from the leading edge in percentage of chord, that is 40%. So we have to input that 40% division 0.40 and enter. See. And last two digit what we have, that is the thickness. This one, this last two digit what we have, that is the thickness of the aerofoil, 21%. Okay, now we have to change the thickness. Default we have 10%, that we have to change it to 21%, 0.21, enter. See, 2421 aerofoil. As soon as we enter our parameter, okay, after typing in this checkbox, okay, and once you enter, then automatically you can see the name of your aerofoil which you have entered, and directly name will get, that is the name of aerofoil NACA 2421, right? So that is what we have in our given data, that is NACA 2421. So aerofoil is done. Now next, what other parameter we have? Next parameter, that is chord 2 meter. Okay, So what we have to do, we have to come to again section plan. Okay, and we have to change this chord. Okay, chord length, how much we have, 2 meter. Okay, the chord length, that is 2 meter, so we have to change this chord length. The default what we have 2.8, that we have to change into 2. Type 2 and enter. Done. Next, what other parameter we have? We have the tip chord length, that is 0.8 meter. Tip chord length 0.8 meter, right? So this tip chord length we have to use here. Yes, root chord and tip chord. Okay, in this section, okay, we have not splitted any of the section for this wing. Okay, because in this given data I have not given any such things that split your model and take a compound type of thing, like that is not given, just like this only, right? So we have to keep same as it is. Okay, which means we should not do any sections for this wing. So now we have to change the root chord length and tip chord length. Root chord length how much? 3.2 meter, and tip chord length is 0.8 meter. Okay, so first I will import this 0.8 meter, that is tip chord length 0.8 meter. Tip chord length 0.8. Type 0.8 in this checkbox, that is tip chord length, and enter. It's done. Next we have the root chord length CR, that is 3.2 meter. See, this is our root chord length, and this one is our tip chord length. Okay, that's what I am typing. So tip chord length is done. Next one is our root chord length 3.2 meter. Root chord length 3.2 meter already. You know the same thing. Once again I will just type 3.2 and I will enter. Done. Okay. After this we have the sweep. Sweep angle is given how much? 30 degree. So what we have to do? We have to change that also. Okay. Yes, sweep default we have 30 only. That's okay. Type 30 once again, no problem, and enter. Done. Sweep angle is also done. See, sweep angle it is varying, right? I don't want to vary in that way. Just I want to keep my sweep angle as per the given data, that is 30 degree itself. So just what I will do, just I will type the 30 degree, that's it, and I will enter. Done. Okay, these are all things done, right? Now we'll check once we have missed any parameter. No, right, everything is done. Okay. mm. Wing reference area 60, that is also done. Span length, wing reference area, yes, that is 60. Type 60 and enter. Okay. Yes. Wing reference area 60 meter square. That is also done. Aerofoil 2421. Aerofoil 2421. That is also done. Okay. Chord length 2 meter. Root chord. Here we have the chord length completely. That is 2 meter. Okay, okay. So here we have to maintain our area. Okay. So what we have to do? We'll use this tip chord and root chord. That's it. Okay. Just we'll keep as it is this root chord and tip quad. Okay, and here just we will type default coordinate whatever we get, let it be. Okay, just we will change the area as per the given data, 60 meter square, that's it. Okay, and in this given data what I have given, tip chord and root chord. Okay, that we will use. Chord we will remove complete chord length, because tip chord, root chord, that both parameter we have, that's okay. Okay, because if we change the chord length here, then again directly or indirectly we are disturbing to our area, right? So that's why default let it be this chord length, that is 2.19 for all chord. Okay, now span is not given, right? In this given data, span length is not given. Okay, so what we will do, we'll just keep as it is default value span, that is 27 we have. So what I will do here, I will just do the span length, 7 point span b, that is equals to 30 meter. So we'll change the span 27 to 30. Enter. Done. Okay. So these all things we got as per our requirement. Okay. And now what I will do, I will do little changes in this. Okay. Uh, Instead of root chord, okay, I'll convert this into just chord length. So we'll use this one now. That is 2 meter. So what we'll do, we'll change this chord 2 meter. And default we got 60. Okay, yes. So now once again we will do cross verifications. Whatever we have the given data, as per the given data, everything is settled in the open VSP or not. Just we will do cross verifications. Okay, because this is your first model, that's why I'm going with very basic thing. So our span is 30 meter. Okay, that's done. Chord 2 meter, area 60 meter square. Okay, so once you import these two parameters, automatically you will get aspect ratio, that is 15. Okay, and next we'll come to section. Okay, section, under this section, root chord. Okay, here we have 3.2 and tip chord 0.8. Okay, root chord 3.2 meter and tip chord 0.8 meter. It means whatever given the data, as per given data everything is settled. So just I will type that also. Yes, root chord 3.2 meter and tip chord 0.8. Okay, root chord and tip chord done, right? And our arrow file, that is 2421, arrow file 2421. Okay, and next, sweep angle. So just come to section and you can see the sweep angle is 30. Okay, which means as per the given data everything is done, only now we have to change the material. Okay, so to do that what we have to do, just we have to shade this. First we have to shade our model. Okay, so wireframe model we have to convert it to solid okay, by using this option, that is shade option. Okay, so default we have material. Okay, this default material we have to change into as per our requirement, that is aluminum based material we have to use now. Okay, so just come to this material and select the material, that is aluminum. Okay, density value and all it is not given, so let it be default because just we are designing the, or we are creating the basic view model, okay, as per the given data. So this is your aluminum based wing model as per the given data. Okay, so now we can see your model with all these views, that is top view, front view, left, bottom, rear side, right ISO, and you can put on screen and you can capture the image. Before that, what you have to do, you have to save this. Okay, go to file and use save as. Select your path, any one path. Just I'll save here itself. Okay, and I will give the name. That is basic wing model. Accept. Okay, so your file will get saved, which means that has been settled in your C drive. And because I have chosen C drive, okay, which means my directory of what I have, that is C drive. Okay, my .vsp file, this model, whatever just now I designed, this model has been saved in this directory C drive. Okay, so the name you can able to see basic wing model 1 .vsp3 .vsp3, that indicates that is your VSP model file. Okay, so this is all about today's topic that is done, that is the creating a basic wing model. So we have created the basic wing model. Okay, this one you can able to see the top view, and you can even capture the image screenshot. Okay, capture in any form, and then you can give file name. If you want to change your width height, then you can change. So this is our .png file. Okay, so that is you can design your any wing model. So yes, so we have done with our basic wing model, that is by using NASA's OpenVSP we have created the basic wing model. This is our basic wing model. So this is all about today's topic. Thank you to all.
Rajinikanth sir?
Sir, done, sir. Today's class done.
Okay, sir. Thank you.
Okay, thank you.